So I'm going to talk about this experiment I did. Broadly motivated by the idea of if you're trying to use small multilayer perceptrons to implement boolean functions, since the neural net is composition of linear boolean functions, the idea of distance to the set of linear functions seems to be an interesting a way of giving structure to like nonlinear functions, because then you could try to make statements like if the function that you're trying to implement is sufficiently far away from the set of linear functions, then you need more than one layer to implement it, right? Like those are the kind of propositions we're trying to establish. So anyway, like here's the experiment. It's kind of I'm just going to explain it using drawing instead of like the code, because like the code is incomprehensible. So anyway, we have, so I think let's say we're doing like this is input dimension, n equals 3 billion functions, so like there's 256 of them. And like this is a VIN, no, it's anyway, there's 256 functions in general, and I think 104 of them, that would be a larger circle actually. I think 104 of them are linear. And so what we did is we take the 104 linear functions and whatever 256 minus 104, I think that's like 152, isn't it? So we form this matrix, and then in each entry, right, so like each row is a linear function, each column is a nonlinear function, and then each entry is the Euclidean distance between the two functions. And so for instance, what you could do is you could then take like the min over all of the columns for a row, and then that would be like a concept of how close the linear function is to maybe I already screwed this up. It's supposed to be the other way around. Yeah, we'll just, like this is non-lin. This is lin. It doesn't technically matter, but so anyway, that would be a concept of how close the nonlinear function is to the. So anyway, let's just look at some results, right? Like, oh, actually no, I should because I didn't actually do it. Like what I did was I took the rows and I turned them into a histogram. So we have like distances. So for n equals 3, you can have distance like up to 8. So like 0, 1, 2, 3, 8. And then just the counts. So like the number of functions at that distance, right? So like I turned that into a histogram type thingy. And then it, so again, these are still integers. So like if you have like a 2 here, you're saying like there are 2 linear functions that I am distance 1 away from, right? And then it turns out that like different nonlinear functions can have the same histogram. And so we collapse all of those, and then we display the results. So this is the results for n equals 4. Like this would be like a sample of the histogram. So like this particular row function, there are 0 linear functions that it is distance 0, 2, which means that it's a nonlinear function. Whereas these guys, since there's one linear function that it's distance 0, 2, that means it's a linear function. And so then if you plot all of that, you get this thing, and it won't let me tab. Yeah, so that is a plot of all of the histograms for n equals 4. And so we can see, that's actually better to look at the numbers. So we go to the numerical representation of that. Down here, let me kill that. Down here, maybe that was unnecessary, but so like down here, these are functions, these are nonlinear functions. There are 0 linear functions that they have distance 0, 2. But for instance, there are 4 linear functions that they have distance 1, 2. So meaning like, if you just flip the output of like a single input, you have like linearized this nonlinear function. So it's kind of what neural nets have to do if they're trying to implement a nonlinear function, like they have to linearize it. And so it seems like there should be some concept of like a capacity of like a layer in terms of the number of, inputs that it can flip to linearize the function. So, so for instance, like we want to say things like functions down here should be easy to implement, perhaps, using a neural net, whereas like functions up here, functions up here should be hard, right? Because this guy is 0, 1, 2, 3, 4, 5. You have to flip 5 bits out of 16 to linearize this guy. And yeah, I also don't know what function that is. It's probably like the parity function. And also like an open question. A big open question is, how does this scale within? So you take the most distant nonlinear function from the set of linear functions, and then you ask, how does that distance scale? Like, because here for n equals 4, the distance is 6, which is also kind of weird. Yeah, so it's like an open question. Let me know if you have any insights on these matters. Thank you.